So in the previous example, we saw that the values of our sequence C sub n tended to the value square root of 2. Another way of saying that is that the limit of our sequence is square root of 2. Now, I'm including a formal definition of the limit of a sequence here using an epsilon definition. This is not a definition that I require you to use on exams, nor will I ask for this definition. So the way that we are going to calculate limits is by translating these limits of sequences to limits of real numbers and functions of real numbers. So theorem 9.1 says that if L is a real number and f a function of a real variable such that the limit as x approaches infinity of f of x equals L, then if a sub n is a sequence such that f of n equals a sub n for every positive integer n, then the limit as n goes to infinity of a sub n equals L. And the beauty of that theorem is that we can use some of our theorems that we've used before. For instance, L'Hopital's rule can apply. Let's see how this theorem works in practice. We're looking at the sequence a sub n given by 3n minus 2 over 2n. So we want to now find the limit of a sub n as n goes to infinity. So the first thing we're going to do is we're going to define our function f of x. So f of x is equal to, and the only thing we do here is we replace the n by an x here. So f of x equals 3x minus 2 over 2x. So then we're going to find the limit as n goes to infinity of a sub n is equal to the limit as x goes to infinity of f of x. That is, if that limit exists. So what we get there is this is the limit as x goes to infinity of 3x minus 2 over 2x. And when you look at that limit, you see that when you try to plug in infinity, you get 3 times infinity minus 2. That gives you infinity, and then 2 times infinity is infinity. So we have an indeterminate form of infinity over infinity. So that means L'Hopital's rule applies. So when we take a look at this limit, we have the limit as x goes to infinity, and then we can take the derivative of the top d dx of 3x minus 2, and then d dx of the bottom, which is 2x. So 3x minus 2, and then 2x in the denominator. And so that is the limit as x approaches infinity of the derivative on the top is 3, the derivative of the bottom is 2. And so the limit of a constant is a constant. And so the final answer here is 3 over 2. So this limit, the limit of this sequence is 3 over 2. Now, when we look at sequences, they oftentimes involve products of numbers. And one way to efficiently write down products of numbers is by using the factorial notation. So the expression n factorial is defined for positive integers as follows. N factorial is equal to n times n minus 1 times n minus 2 times etc., all the way down to 3 times 2 times 1. And 0 factorial is defined to be 1, to make everything work in the end. And one thing, when these expressions show up, factorials, they can oftentimes be simplified. So here's an example of an expression that we want to simplify. N plus 2 factorial times 5 factorial divided by n factorial times 7 factorial. So what we do here is, let's write out n plus 2 factorial. So that's n plus 2 times n plus 1 times n minus 1 times n minus 2, and then all the way to 3 times 2 times 1. Okay, so that's my n plus 2 factorial right here. Okay, now let's take a look at the 5 factorial. What is that? That's small enough so that we can just write that out all the way. So that's 5 times 4 times 3 times 2 times 1. Okay, and then let's take a look at the n factorial. By definition, that is n times n minus 1 times n minus 2, and then all the way to 3 times 2 times 1. And then finally, our 7 factorial, right here, we can write that as 7 times 6 times 5 times 4 times 3 times 2 times 1. So if we have that total fraction, there's a lot that we can cancel out. So for instance, we see a 5 factorial right here on the bottom, right? This is a 5 factorial. And so this will cancel with the 5 factorial on top. So we can cancel that out and then cancel that. Now here with the n plus 2 factorial and the n factorial, we see that they both have an n factorial. So this part of the blue expression, that is n factorial, and so that one cancels with the n factorial on the bottom. So now let's collect what is left of our fraction. So on the top, we have n plus 2 times n plus 1, and then times 1, right? When you divide this out in the numerator, we just have 1. On the bottom, the n factorial completely disappears, and that is now a factor of 1. And then we're left with the 7 and the 6 on bottom. So this fraction can now be completely simplified to, you don't need to FOIL this out, but if you want to FOIL it out, you get n squared plus 3n plus 2 over 42. And that expression looks a lot simpler than the expression in the original problem.